Hey there, welcome back to our course on advanced quantum mechanics. This is lecture 25. Remember that when measuring an observable f hat, so when measuring an f hat, the outcomes of the measurement procedure are always numbers in the spectrum. So always find values from the spectrum of f hat. These are the only possible outcomes. We derived that in the previous lecture. Now, what is the probability for finding a particular outcome? What is the probability for finding some outcome, let's say Fm? Probability for finding the outcome Fm in the measurement of the observable f hat we derived is equal to, if psi is the state in which the system is currently, then it's the expectation value of this observable here, where q hat is defined to be the operator obtained in this way, assuming that the spectrum of q hat is non-degenerate. So we assumed that in the previous lecture, that each eigenvalue has only a one-dimensional eigenspace and not a higher dimensional eigenspace. So we will need to generalize this now. Before we do, let's look a bit more closely into what is going on here, into this so-called measurement-induced state collapse. So what we have is that the system starts in state psi, and after the measurement, it is in the state psi after, which is, well, one of those eigenstates here, one of those states in which f hat is diagonal. Now, how can we describe the map that describes this collapse, where psi goes in and Fm comes out? Now, what we observe is when we apply q hat onto the state psi, then we obtain what? Well, we obtain Fm psi, and this is a state which is proportional to Fm, which is our psi after, which is psi after. So overall, this tells us, apart from minor details such as the normalization, this tells us that the operator q hat is involved in describing the collapse of the state psi that the system had when we performed the measurements into the state psi after that the system has right after we performed the measurement. So in fact, we can therefore write using the Q hat, we can write that the psi after is equal to, and I'll explain in a sec why we need this particular term in here. And then we have Q hat psi. Okay. Why is that? Well, Q hat acting on psi gives us the state that we want, namely the psi after. Remember, we want to describe the map from the state before the measurement into the state after the measurement. And assuming that a particular measurement outcome Fm is being measured here. So what we have is that Q hat, according to the previous calculation, produces the state psi after, except that the normalization isn't quite right. And so that's, we just have the proportionality here, right? It's Fm up to that prefactor. So what we can do is, we can say that psi after is obtained by applying the projector Q hat on psi, and then we simply divide by the length of whatever the length of that vector is. And then we know that the whole thing is normalized. So this is a normalizing factor. Normalizing factor. Now, what I want you to notice here is that the equation psi star is nonlinear in psi. If, for example, we chose here the vector psi to be replaced by psi1 plus psi2, well, then this part would be linear. We just have a linear operator that acts then on psi1 plus psi2. But this thing is not linear. I mean, this thing is not, the whole thing is divided by psi. So here we would have the Q hat of psi1 plus psi2. And that would not linearly give us a result psi after. Or view it this way, if we multiply psi by lambda, then we are not multiplying psi after by lambda, because this lambda would also appear down here, and so it would cancel out. So equation star is nonlinear in psi. And that means that there is no unitary map that would describe how psi goes into psi after. This means there is no Schrödinger time evolution that would describe how psi goes into psi after. Which is why some authors have been worried about this and thought, this means that something is going on in the measurement process that is beyond Schrödinger quantum mechanics. And since the Schrödinger picture is equivalent to any other picture, something is wrong or something is missing in ordinary quantum mechanics, and we have to describe the process of collapse as being external to quantum mechanics or having to be added to quantum mechanics. As you will later see, that's not the case. We can, in fact, describe this collapse by doing very carefully the following. We take our system here, and then we take the measurement apparatus over there, measurement apparatus. And the measurement apparatus, no matter what it is made out of atoms, and therefore it also obeys the laws of quantum mechanics. The whole thing is a quantum system. And then when we look at the combined quantum system of the two of them, then we see that what we normally think of as a measurement, namely that the measurement apparatus measures something about the system, from this new perspective, where simply this is a quantum system and that is a quantum system, this thing that would normally be called a measurement can also be called simply an interaction. We simply have two quantum systems that interact with each other. And interactions can be described in a unitary way, entirely within quantum mechanics. So the quantum mechanics of the big system describes the interaction between the two subsystems, and that's just all following the Schrödinger equation of the big system. It's just that when we then focus on the subsystem alone, then it looks as if something nonlinear went on. Then it looks as if something non-unitary went on. But that's just because we opened up the system to being interacting with the measurement apparatus. So it's one of my goals later in this course to explain exactly how to move from the one point of view to the other, back and forth. So measurements are interactions, and interactions are measurements. There's some subtleties with this, but we will cover them as well. Now let's come back to the task at hand. Remember that so far we assumed that the spectrum of our operator Q, the spectrum of our observable f hat, is non-degenerate. But what if it is degenerate? So now what if the eigenvalues of f hat, I mean, they don't all have to be degenerate. What if eigenvalues of f hat are degenerate? Let me remind you of what that means, that the eigenvalues are degenerate. But what it means is that for one eigenvalue, there's an entire multidimensional eigenspace. So this would mean, i.e., there exists a whole set of eigenvectors for the eigenvalue fm, and since there are many of them spanning an n-dimensional eigenspace, let's just choose an orthonormal basis in that eigenspace and label the basis vectors fm index a. Fm means the eigenvalue, and then since we have plenty of eigenvectors, we label them a. Here a is running from 1 to n, let's say, if our eigenvalue fm is n-fold degenerate. So all with same eigenvalue fm. So what we have is that f hat acting on one of those vectors, fm subscript a, is fm subscript a, right? So our fm eigenvalue is degenerate in this sense. Then what is the probability for finding the value fm? So then the probability for finding fm is what? Well, we previously introduced the operator q hat for that purpose, and we can still do this also in the non-degenerate case. Namely, we define q hat to be the sum over a equal 1 to n f m a f m a. If our eigenvalue fm is not degenerate, if there is only one eigenvector, then there is no sum. We only have one term, namely fm, as we discussed in the previous lecture. All right, so we define this operator q hat here, and then one can show very simply that q hat dagger is q hat. I suppose you can already see this. And also q hat squared is equal to q hat. You just have to multiply that series on the same series again, and then you get Kronecker delta at Kronecker delta, and then one of the two sums goes away, and you're left with just one sum, and it's the original Q. So what this means is that Q hat is a projector. And what that means is that the spectrum of Q hat contains only 0 and 1. So therefore, outcomes of Q hat measurements are only 0 and 1. If you can build a machine that can measure Q hat, the output will be 0 or 1. And such a projector here is called, let me get just a definition, a projector Q hat is called of rank n, as is the case here, if the dimension of the space on which it projects, so the dimension of the image of Q hat is equal to n. Now, as before, we can now answer the question, namely, therefore, well, let me just go back to what we said just before. The outcome of Q hat measurements are only 0 or 1. And when do we get a 1? We get a 1 when we find one of those states, one of those eigenstates that have that particular eigenvalue. And otherwise we find 0. So therefore the proportions of 1 in that we find in an ensemble measurement tells us how often we find one of those eigenstates. Or more accurately, how often we would find the eigenvalue Fm of the observable Fm. So therefore, assume system is in state psi. Then the probability for finding the eigenvalue Fm is equal to the expectation value, again, of our projector Q, which in this case now is the sum A equal 1 to capital N of psi, and then Fma, Fma psi. Now, this can also be interpreted in terms of the Born rule. Interpretation. Well, you see, each one of these terms here what we have is that psi, Fma, Fma psi is, by the Born rule that we covered at the very end of the previous lecture, the probability to find the state FMA. So therefore, the sum from A equal 1 to n is simply the sum of the probabilities to find any one of these degenerate eigenstates of our observable eigenstates with eigenvalue Fm. So then what is the state after the measurement? State psi after the measurement. And finding the state F and finding eigenvalue Fm. I should say measurement value Fm, which is the eigenvalue, of course. Finding measurement outcome that we call Fm. So if the system is prepared in a state psi, and then we perform a measurement of F hat, and we find as the measurement outcome the eigenvalue Fm, then we can ask what's the probability for this to happen. Well, we just calculated what the probability for this to happen is. It is this. And if it occurs, if we do find the eigenvalue Fm as the measurement outcome, then after we found that, the state of the system is going to be psi after is equal to, and then it's the same formula as what we had before. You apply your Q hat on psi. This is the normalizing prefactor, and then you can apply the Q hat operator onto psi. If you apply that, you're projecting again onto the suitable eigenspace, which is now multidimensional, and this will make the norm right. For more, I refer you to an exercise, a homework that's related to this. Okay, so more generally now, let me mention that the Q hat that here arise for each possible measurement outcome of some observable F hat can arise also differently, namely more generally. As you may have suspected, these Q hat are super important. These Q hat are 1-bit observables. These are describing the smallest possible measurements you can make when you measure only at most 1 bit of information. So more generally, every projector, whether it arises in the way that we discussed before or not, every projector P hat is a 1-bit observable. Again, why is it an observable? Well, observable because since it's a projector, we have that P hat is equal to P hat dagger. So it qualifies as an observable. Why is it a 1-bit observable? 1 bit. Well, that's because the spectrum of P hat is taken from, well, let me put it this way. It is contains only 0 and 1. 0 and 1. It can contain only 0 and 1. In principle, it could contain only zeros or only ones. The identity operator is a projector because it's self-adjoint and it squares itself. The same is true for the 0 operator. So 0 and 1, 0 and the identity operator are also projectors. But of course, these are not the ones we have in mind here. All right, so 1 bit because the outcomes are only zeros and ones. So the measurements just give us a 0 or a 1. 1 bit of information and at the max. So let me show you that there are useful examples of this, other than the ones that we needed to calculate probabilities for outcomes to happen above with the f-hat. So examples. Let's say we look at the hydrogen atom and we choose p-hat 1 to be the sum n equal to 7 to 12 of En where these are energy eigenstates. Then it doesn't have to be the hydrogen atom, right? Could be any system really, any system with discrete eigenvalues, with discrete energy eigenvalues. Well then, what is P1 bar? Well then this is the probability for the energy to be found between E7 and E12. And for another example, let's say the free electron in 1 dimension. Well, let's define your projection operator P2 to be the integral from 0 to infinity of P momentum eigenstates dp. In this case, what is P bar, P2 bar? Now this is the probability that the electron is moving to the right. Why is that? Well, because it's the probability for the momentum to be a positive momentum, which is to say the particle is moving to the right. Okay, so you can cook up observables for all sorts of things in this way. And these are just the simplest one with 1-bit information. I'm sure you can come up with observables that have more bits of information. You just need more eigenvalues. The log of the number of the eigenvalues, the log to basis 2 of the number of different eigenvalues is the number of bits of information that you can maximally extract from a measurement. Okay, so what's the picture so far? The picture of collapse so far. Let's choose the Schrödinger picture. We could use any other picture, but for this kind of study, the Schrödinger picture is the most convenient. Choose the Schrödinger picture. Now, in that case, all the time evolution is in the states. So assume state psi naught at time t naught. Then, what's next? Then we have a Schrödinger evolution. Then we have a Schrödinger evolution. And by Schrödinger evolution is meant time evolution of the state according to the Schrödinger equation. So then we have a Schrödinger time evolution. So we have a time-dependent state vector until we do a measurement f hat from time t1 to t1 plus epsilon 1. Because every measurement really takes a little bit of time at least. Nothing happens really instantaneously. So then an outcome is found. And that outcome may be called Fm, so an eigenvalue is found. With some probability, right? With probability, with the probability given by probability of finding the eigenvalue Fm equal to psi of t1, which is the moment in time when the measurement of f hat starts, starts. And then it's q hat psi of t1, right? It's the expectation value of the q hat, where the q hat is equal to the sum a equal 1 to capital N of Fm A, Fm A. Assuming that our state is degenerate, if the eigenvalue, assuming that the eigenvalue is degenerate, if it is not degenerate, if Fm is not a degenerate eigenvalue, then there is no sum, it's just Fm. Okay, so that's the outcome that occurs with a certain probability, and here's how we calculate it. Well, then when the measurement is over at time t1 plus epsilon 1, the state is psi of t1 plus epsilon 1 is equal to, remember how that works, we apply the q hat operator onto the incoming state, psi of t1, the state that the system has when the measurement hits. Now, in principle, this gives us the right state, but it's not normalized yet. So we have to divide by the norm of that state, q hat psi of t1. We have to divide by the length of it. Right, so that's the state after the measurement. What then? Well, then Schrödinger evolution again. Schrödinger evolution. So we have again psi of t until at time, or from time t1, from time to t2 to t2 plus epsilon 2, until from t2 to t2 plus epsilon 2, we measure again. But now we measure some other observable g hat. Well, we find an outcome. Find an outcome, and that outcome has to be some number from the spectrum of g hat. So we find an outcome, let's call it gn, and with probability, with the probability of finding the value gn, so this is in the spectrum of g hat, probability of gn is equal to the state at the time t2 when we start the measurement, and then we have another q hat operator and psi of t2. So we have the expectation value of q hat again, right? So this is q bar. But what is our q hat now? Well, now, and maybe I should call this a q hat prime or something. So this now is, because it's not the same as the q hat above, this is now the sum, let's call it b equal 1 to capital M, and then we have here g n b, g n b. So these are the eigenvectors. This is a set of orthogonal eigenvectors, orthonormalized eigenvectors of g hat, all of them with the eigenvalue gn. If the eigenvalue gn is not degenerate, this is not a sum, there's just one term, as usual. So now, state at t2 plus epsilon 2 is then, well, is then what? Well, then we have to do this projection again. So we obtain that psi of t2 plus epsilon 2 is equal to, well, we apply this q hat prime operator now onto the state that was there before the second measurement, namely psi of t2. And then that's the correct state, but we have to still normalize it, so we have to divide by the length of that state. So that's q hat prime acting on psi of t2. All right, and then what? Well, then we have again Schrödinger evolution. Schrödinger evolution, that is to say, evolution according to the Schrödinger equation, and psi is the state of our system is time dependent. As I mentioned before, later we will see that there's another way of describing what we just discussed. Namely, on one hand, we can say, as we did just now, that we measure, we time evolve the undisturbed system, and then we measure it again, and then it's time evolving freely according to the Schrödinger equation, and we measure it again, and then it's time evolving freely according to the Schrödinger equation, etc. And during the measurement process, something nonlinear is happening, something that looks like a wave function collapse or like a state collapse. But between measurements, everything is evolving unitarily. That's one way of looking at it. Another way of looking at it is that we say, well, we have the measurement apparatus, or we have several measurement apparatuses that interact with our system sometimes. And then they decouple again, and then they couple, they decouple, and they couple. So the coupling is an interaction, the interaction that performs the measurement. The measurement is an interaction, the interaction is a measurement. So you see where this is going. We will have to study how two quantum systems interact, or how one quantum system can be broken into two subsystems which then interact. Okay. Now, there's a very important special case of this. So what do I mean by this? By the evolution we just saw. We prepared a system in some state, then it evolved according to the Schrödinger equation. Then we performed measurement number one. Then we allowed the system to evolve according to the Schrödinger equation independently. And then we hit it with measurement number two. So we measured an observable f hat, and then a while later we measured an observable g hat. What if we choose to measure the second measurement? What if we choose to measure g hat pretty quickly after measuring f hat? What if we choose there to be so little time between measuring f hat and g hat that there is no significant Schrödinger evolution between the two measurements? What then? This is a very important special case. Special case. G hat measurement so close, or so soon after f hat, so soon after f hat measurement that there is no significant Schrödinger evolution of psi between the two. Between the two measurements. In this case, if we do this and we push it so that we measure G basically right after measuring F, can we say that we measure G and F at the same time? Can we say that we measure them simultaneously? Then, can we say that we measure G hat and F hat simultaneously? Well, the answer is it depends on whether the G hat and F hat is equal to 0 or not. Now, I assume you know that, but let's see exactly how that happens. Case 1. Let's say F hat and G hat do not commute, let's say. First case, they don't commute. So therefore, Q hat and, well, let's just spell it out. Therefore, the Q hat and the Q hat prime generally do not in general commute. So therefore, the two collapses do not commute. What do I mean by that? Remember, if psi is the state of the system, then you perform a measurement, you get some outcome, and what is the state afterwards? It's q hat, right? After the f hat measurement, the state of the system is q hat acting on psi, up to the normalization prefactor. And then if we apply afterwards the g hat measurement, then find an eigenvalue gn, then again there is a projection operator q hat prime that needs to be applied in order to describe the projected state then. So after we measure f hat and then g hat, the state collapses into this state up to some prefactor, some normalizing prefactor. If, however, we instead measure g hat first, then this is the projector that acts first. And then we have the projector q hat that acts second, and then we just have to normalize the state. But because they're not commuting, these can be different states. They can be completely different states. So therefore, no matter how carefully we try to measure f hat and g hat at about the same time, one of them got to be first. It does actually matter a lot whether we measure one or the other first. And by how much the outcomes differ doesn't depend on how close the two measurements, f hat and g hat, are in time. So therefore, we are never allowed to say that we measure f hat and g hat at the same time. It doesn't make sense, because you have to specify whether you measure this or you measure that. They are not the same. So therefore, ordering does matter. Order of the measurements does matter. And therefore, there is no such thing as saying that we measure them simultaneously. Therefore, cannot measure simultaneously. It just makes no sense. All right, case 2. It's the only other case, of course, where f hat and g hat do commute. So therefore, we have that the q hat and the q hat prime commute. Remember why that is? It's because they're diagonal on the same basis. So, therefore, the two collapses commute. Oh, maybe I should say something more about what I just said. I said why, and then I answered because they're diagonal on the same basis. I didn't mean to say that the q hat and the q hat prime are diagonal on the same basis. They are, but that's beside the point. I wanted to say that from the commutativity of the f hat and the g hat follows the commutativity of the q hat and the q hat prime, because these two guys are diagonal in the same basis because they are commuting. And from that, because the q hat is just a part, is built out of a part of that basis, is projecting onto, I mean, the q hat is diagonal on the same basis as the f hat, the q hat prime is diagonal on the same basis as the g hat, and that's why those two guys also have to commute. Also, okay, so the two collapses commute, which is to say that if we measure first f hat, so we have the q hat, and then we measure the g hat, and so we have the q hat prime, then this is giving us the same vector as if we apply q hat prime and then q hat. That is to say, if we measure g hat first and then f hat. So therefore, we can measure them at the same time. So we have that if two observables commute, we can measure them at the same time, no problem. Well, if you can do that with two, can we do it with three? Yes. In general, we can measure any number of commuting observables if f hat, I'll call them f hat superscript I, if they all commute with each other. For all I and j. Now, let's do that. We then obtain let's say any number, let's call it, give it a name, R. Any number R of commuting observables. We then obtain R outcomes of the measurements. We obtain R outcomes, and let's give them names. Let's say these outcomes are called F superscript I, denoting the variable, that the observable that we measured, and then M. So this is, of course, an element of the spectrum of our ith observable. And M indicates that it's one of the eigenvalues of this observable. Now, their projectors are sometimes the software just opens up a menu. I don't intend to do that. So the projectors are now no longer just Q and Q prime, but we have a projector for every one of these observables. So their projectors are then, let's call them Q hat superscript I and M, because they are, you know, special for one of these eigenvalues there. Then they are sum over A equal 1 to N I, and then F I M A F I M A. So we are allowing here again that the eigenvalues may be degenerate. Okay, so instead of having Q and Q prime, we now have all of those Qs. And knowing these projectors, we can now also calculate the probability for various outcomes. But let's ask, what is the state after that collapse? Well, what is it? We have that psi, after measuring all of these states simultaneously or very closely spaced in time, right, one after another, so that there's no significant Schrödinger evolution between them. Well, this is then equal to, well, what you get when you apply all those projectors, right? So um, let's write it as Q hat I, and the product of all of them, so I equal 1 to R, because we have that many, and then we apply that onto the state psi that the system was originally in. Now I can write it as this product like this without specifying in which order we perform these projection actions on psi, because they commute anyway. So it doesn't matter. And then this is the right state, but not yet of the right length. So we have to divide it by the length of this exact state. 1, and then we have Q hat I. Psi. Okay. So that's the state that the system will collapse into after we've measured all these commuting observables F hat I simultaneously. Now, how far can we push this? How many commuting observables are there? And can we do that for an ordinary quantum system of an electron? You know, how many of those F hat can we find? Or how many should we find? Well, remember that if you have a quantum system and you have an observable whose spectrum is not degenerate, well, then there's a very convenient way to write down a Hilbert basis, because every eigenvalue describes exactly one eigenvector, and so you have a convenient description in the eigenbases of that observable. Now, however, we have started to look into the case of observables that have degenerate eigenvalues as well. And for those, it is useful to sometimes measure more than one. Namely, how many? Well, let me give you the definition. The definition is, we say we reach a maximum set or maximal set of commuting observables let's call it maximal set of commuting observables if these projectors here, if these products of projectors here are all of rank 1, if the projectors that we obtain, namely the product I equal 1 to R of Q hat I, is rank 1. This means that we can use this maximal set of commuting observables to conveniently label a Hilbert basis in our Hilbert space. Let me explain how. First, when is this useful? When useful? When we have an observable with degenerate spectrum. Let me give you examples. So examples. Let's say a MSCO, a maximal set of commuting observables for an electron is the three, let me put it this way. F hat 1 could be chosen to be X hat 1, then F hat 2 can be chosen to be the second position operator, and then, for example, this could be the third position operator. Or we could also choose F hat 1 to be X hat 1, and then F hat 2 could be chosen to be P hat 2, for example. And then F hat 3 could be chosen to be X hat 3 again. You see, why would we want that? Imagine we wanted to work with just the position operator X hat 1 for quantum mechanics in 3 dimensions. Well then, knowing the eigenvalue X hat 1 doesn't tell you what state you're in, because the eigenvalue, every eigenvalue of the operator X hat 1 is highly degenerate. And similarly for X hat 2, P hat 2, etc. So we couldn't, as we did so far in this course, simply say we take a self-adjoint operator and then we label its eigenbases by the eigenvalues. No, we would have to invent other labels as well, because the eigenvalues don't label the eigenvectors. There are more eigenvectors than there are eigenvalues, so we have to introduce extra labels. And instead of inventing some arbitrary labels, what we do is we take other observables as well, which, if they commute, can help us provide these extra labels being the measurement values or the eigenvalues of these other observables. This also comes up, for example, for the hydrogen atom. There, we could choose for an MSCO, maximal set of commuting observables, we could choose, for example, the Hamiltonian and then the angular momentum squared, and let's say the third or first or second component of the angular momentum vector. And then you see, same thing, if we just pick an energy eigenvalue, then that doesn't tell you yet which eigenvector it's going to be, because for every energy eigenvalue, there are plenty of, there's a high dimensional eigenspace for each energy eigenvalue. And then similarly, for the free particle, so let's say we have a free electron, there we could choose, for example, again, the Hamiltonian of it, and then we could choose P hat 2 and P hat 3. Of course, we could replace the Hamiltonian by P hat 1, but we can also write the Hamiltonian here. The Hamiltonian is P vector squared over 2m, and P vector squared commutes with P2 and with P3. All right, so if we do this, if we choose a maximal set of commuting observables, f hat 1 to f hat r, then the collapsed state after the measurement of all these commuting observables is an eigenvector to all of the observables f hat I with eigenvalues f hat I, no, without the m, without the hat, of course, right? With these eigenvalues. Namely, we have that f hat I, so the ith observable, acting on the collapsed state, let's call it psi after. See, we can do tricks like this. So we have psi after. That's not what I wanted to do. I wanted to put it here. Okay, so this is equal to f hat I, and then the mth eigenvalue acting on psi after. And well, this is true for the first one. And then the same is true for the second one, f hat 2 psi after equal to f. No, sorry, there is no hat here because this is meant to be just an eigenvalue. All right. Well, this should be, okay, let's say m1, and this would be m2 psi after, etc. So it is natural to denote this vector psi after as by psi after equal to, and then we list the eigenvalues that it has with regard to the observables that we measured. So we write this as f 1 and then m1 and then f2 and then m2, etc. up until f r and then m r. And the requirement for a maximal set of commuting observables, that the product of all the projectors gives us a projector of rank 1, that requirement is what makes that unique. There's only one vector that is labeled by this one combination of eigenvalues. For every combination of eigenvalues, there is exactly one vector. That's why we can write psi after in this way. So remember, this is needed only if we are looking at an observable, if we want to measure observables that are degenerate, that have degeneracies. Otherwise, no need for that. The eigenvalues completely label the eigenvectors. And so in particular, please don't think that three-dimensional quantum mechanics always needs three observables in order to pin down pin down the basis vectors. No, you could have a million electrons in a box, and you measure one observable, and then the eigenvalue of that observable would describe everything about this million electron system here. Because remember that if the observable has a non-degenerate spectrum, then this one measurement outcome, this one eigenvalue, will single out which state the system is in. Very convenient. In practice, though, those observables that have a non-degenerate spectrum are rare. And that's because of the symmetries that we have in nature. the x1 and x2 and x3 operators commute with each other. And similarly, the momentum operators commute with each other. And that has to do with the flatness of space-time, of space. It's a result of the symmetry there. And so, because it is, for symmetry reasons, advantageous to work with the position operators, also because they are easier to measure than other operators and momentum operators, we work with those. But then they have highly degenerate spectra. There are plenty of vectors that are position eigenvectors with a particular eigenvalue for the first position operator. There are plenty of them. There are infinitely many of them, because you haven't specified yet what the other eigenvalues would be for the other observables. So we need the procedure that we did today just for the purpose of dealing with observables that have some degeneracy, and then wanting to use the eigenbasis of this observable as a Hilbert basis to expand the calculations in. So for example, let's say we choose the H atom again. Well, there, of course, we have a maximum set of commuting observables in the form of the Hamiltonian, then L hat squared, and L hat 3. So what's going on there? Well, we observe, I'm assuming you know all these things. I just want to show you exactly what's going on behind the scenes. So we observe that the spectrum of the Hamiltonian is degenerate, which means that for one eigenvalue of the energy, there are plenty of eigenvectors. So therefore, we cannot simply say that En is a basis. No, because there is no single eigenvector. There are multiple eigenvectors for each eigenvalue. So what do we want to do then? Well, then in principle, we have to introduce another index, lambda, which labels a basis in the eigenspace, the multidimensional eigenspace, to an energy En. Now, how shall we choose that basis there? How shall we choose that label? And we could choose it any way we want, but we could also choose to measure also L vector hat squared. We could choose to measure that too, simultaneously. As we now know, we can. And this means that they are diagonal in the same basis. L hat squared is diagonal the same basis as the Hamiltonian is, which means that if you look at the Hamiltonian, it can be written in this way. There is E1, 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 and then there's E2, 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 and then it goes on with E3, etc. Right? Each eigenvalue is repeated in its eigenbasis, is repeated as many times as there is a degeneracy in that eigenvalue. Now the L hat squared is diagonal in the same basis, but the eigenvalues don't have to be the same all throughout here, right? And that allows us to put another label there. So we will also have that L hat vector squared acting on our En. And now let's choose another name for that label here. Let's say L is equal to L times L plus 1. Remember, this is how this works with the angular momentum, acting on ENL. Now, I left a little bit of space here because, as it turns out, you need another label, because if you look at the diagonalization of L hat squared in the same basis, then you find that sometimes on the diagonal, you have some neighboring eigenvalues that are the same of H, but also eigenvalues of L hat squared are the same. So we still cannot completely resolve. And that's why we also then introduce the L hat 3. Doesn't have to be 3, at 1 or 2 would also do. And then we obtain here 3 labels. And these now are unique. So if we diagonalize all 3 operators at the same time, each one is a diagonal matrix. And every basis vector is eigenvectored to H hat, to L hat squared, and to L3. And if you just tell which eigenvalues our vector has with respect to each one of these 3 observables, then this points to exactly one eigenvector. So this is then a maximum set of commuting observables. All right. I hope that wasn't too tedious. I just wanted to make sure that this is absolutely clear, because sometimes this can be confusing and sometimes people go over that too fast. There's one more thing. So last, the collapse produces the state. Remember, we start with psi, and then we have the q hat, act with q hat on it, and then we have to normalize the state by dividing by q hat psi. So this is our psi after, right? Let's assume we just measure one observable now. Then the thing is, that's not quite unique. I simplified it a little bit, because really we could also put here an arbitrary phase e to the power I alpha. It wouldn't change it, because the modulus is not changed by multiplying the alpha in R. By multiplying a state vector by e to the power I alpha makes no difference. So I just wanted to indicate that the state collapse is ambiguous up to a phase. We will return to that phase later on when we study the state collapse, not from the point of view of happening because of a measurement, but from the point of view that it happens as the result of the interaction between 2 quantum systems, where it's no longer really a collapse. And then we will briefly see how this issue with the phases is resolved. But remember that in any case, the phase normally doesn't matter at all, because when you calculate any prediction, f hat, then it is given by this. This is always how we predict anything in quantum mechanics. And if you take your state and you multiply it with a phase, then this doesn't make a difference. I think we mentioned that at the beginning of the course. So this is unchanged, or independent of alpha. Yeah, I don't have to write that, right? It's independent of alpha. Okay, so this is as far as we get today. See you then.